Jian Chow.
Very good.
Very good? Okay. Dr. Chow is the Cardis Collins Professor at Northwestern, Director of the Northwestern Initiative for Manufacturing Science and Innovation, and Associate Vice President for Research at Northwestern University. She was at the National Science Foundation as a Program Director for 2 years. Professor Chow is an elected fellow of SME, SERP, and ASME. Her major awards include the Charles Russ Richards Memorial Award from ASME and Pi Tau Sigma, SME Frederick W. Taylor Research Medal, ASME Blackall Machine Tool Engage Award, and the NSF Career Award. Also, Professor Chow is the Editor-in-Chief of the Journal of Materials Processing Technology, and she has served as the President of the SME North American Manufacturing Research Institute and Chair of ASME Manufacturing Engineering Division. So without further ado, please welcome Dr. Chow.
Thank you very much, and thanks for the invitation. What I'm planning to do is to talk about the research work has been conducted in our lab called Advanced Manufacturing Process Lab. It's interesting, right? When you started with the M, M could be metal, could be many different things, materials, so it didn't change the acronym that much, but the essence of the work actually has been evolved. So you will see that in our lab we do not just metals but also composites. Today, so here people are graduate students, right? Or graduate students any undergrads? Great. All right. So when you look at the design manufacturing, really just to add the manufacturing, what I see is you combine the idea materials and of course you use energy, and then you add through the design and manufacturing, you change the form, add value, change the compositions. So I had some kind of conversation with David around the lunchtime, and so how do you view manufacturing, right? I view this as a really integration platform. There are many different science and technology goes into that. If you look at, for example, this is from the Advanced Manufacturing Office, a lot of employment, PhD employment, R&D, particularly half of that is in the manufacturing sectors, okay? So for this crowd, I don't think we need to emphasize too much. Everyone understands the importance of that. So in our lab, basically it's co-directed by me and also my colleague, Corey Aitman. And we have, okay. We have three strategic areas. One is looking at flexible fabrication processes. The second one also quite some work looking at scalable manufacturing process for surface engineering. And the third one is digital manufacturing cyber-physical systems. And so when you look at those three, and each one actually requires a little bit different in terms of students' background. So for flexible manufacturing, let's talk a little bit faster. What we are doing is a lot of work I'm going to talk about today is here to look at double-sided incremental forming process, which is a diless forming process to make sheet products. And associated with that, we also have electric-assisted ones to enhance the formability of the metals. And the second category where you look at the flexible manufacturing processes, obviously, is additive manufacturing. So here, we made our own instrumentation called additive rapid prototyping instrument right here. Has very little resemble with those commercial ones, because what we want to do is to tap into the system such that we can change the control, we can change the flow rate, we can change the laser power, we can monitor that, as well as to do the in situ metrology. So what you see here is, for example, right here, this is the primary deposition, but the secondary arm is doing all sorts of different things. So my student Sarah Wolf, actually the one that I mentioned to you today, is actually the one who started when we built up these things. So the process that we are looking at particularly is the direct energy deposition, which is, powder blow and type of the additive. So here is just the first one when we try to make an M. Today I'm not going to talk about this. And the other part when we look at the manufacturing is another big project that we have is on the composites forming. So the flexibility comes in is when you try to design the composites. You can actually design in terms of the epoxy matrix and the fiber, the woven pattern, the fiber volume fraction, and many other things you can design. And the question is how these kind of design at the base, at the material level, impact the process capability, and how the process, when you try to do high rate processing and then eventually change the material properties of the performance. So we have an ICME type of the approach with integrated computational materials engineering approach, try to link this from nano level all the way to the meter size level. And as you can see that there are a lot of people working in this area. So this is overview, so I'm not going to talk about this either. And the second category is scalable manufacturing processes for surface engineering. And the surface engineering, in our case, when we define texture, we define the texture as a geometric features on the surface, okay? And typically around the micro size. One of the things that we have shown here on the plot is that if you put the texture on it, it can help to reduce the friction. So this is a percentage of the friction reduction when you have the metal-to-metal contact. And this is like up to 40%, depends on the contact pressure as well as the sliding speed between these two. Another applications could be looking at, on the drill bits. And this is drilling titanium alloys, Ti64, and without the textures, it wear out really fast. And this is with the texture. And then we are putting the texture around the very small margin areas. And my colleague, the newest colleague that, well, probably people here know the story. We tried to get David, but he left and came over here. So we have this newest colleague who's doing the surface texturing. And what you see here is he had a texture one side and the other is on the flat one. And then you see the one with the textures, the water condensation happens really fast. So this could be application for, collecting water in desert even, and some other applications. So surface texturing has many different applications. These are just a few that, I'm showing. But then the question is, how do you make it scalable, fast manufacturing the textures on metallic surfaces or some other, materials? So one of the things you can do is actually machining. So this is mostly Corey's work, my co-director of the lab. And so he's a machining expert and looking at when you have two piezo and then look at the resonant mode and then do the texturing. And this is the one that we jointly developed, is to do the laser texturing. And for example, this is on needles, and trying to also reduce the force, reduce the insertion force for the needles or for the surgical tools. Okay. The other one you can do it is actually also on the polymer side. You can do this is actually a near field kind of the derivation of the electrospinning one. What you see is actually a fiber right here, and then you can actually deposit beads in a very ordered fashion. So this is an image from a high-speed camera. What's also interesting is that when you come back to the second layer, the drop of the beads actually line up right on top of each other. So this is something very interesting happening. So those are the projects going on with the surface engineering. The other slide which I mentioned is the cyber-physical system. And here, if you think about the general manufacturing, how it's being processed, previously, very early stage, everyone is doing their own kind of cottage kind of manufacturing. And then it comes with the mass production, which is Henry Ford model. And then going to the future, particularly with additive coming in and many other flexible manufacturing processes, robots coming in, smart ones, the mixture is going to be the high rate manufacturing plus the rapid and distributed manufacturing, what we call it. So we wrote actually this paper back to quite a few years ago, before this distributed manufacturing has been a concept adopted by the majority people. And now when you talk to, for example, DoD, and they are really looking into the distributed manufacturing model, and how do you connect these different things together. So one of the projects that we are working with, also with the Champagne colleagues, is to, when you think about all these different capabilities, and how do we create a kind of the internet to create all these different resources together, and then you can also manage the servers, do the routine optimization, and put everyone on the same platform. So when you have small businesses here and there, how do you get their extra manufacturing capability on the same platform when you can do also the certification and the resource. So that's one aspect of the cyber-physical system. The other aspect of the cyber-physical system is also the predictability, right? So when you do the computational modeling, how do you know what the part that you are making is exactly the quality that you are making? So that's another, so this one was funded by DFDI, and then there's also NSF projects going on in those areas. So a lot of these things cannot happen without students. We have, in our group, we have 2 parties every year. Sounds like fun. And one is in the winter time, another one is in the summertime. So this was one of those when we have it in the house. I was particularly proud of a lot of ladies in our group. And that's another one. So with the, this is my colleague Emma, co-directed, and Sarah is right here, and we have the others who couldn't make it to that party. Okay. Okay, with that, it gives you overall kind of portfolio about what we do as the manufacturing process lab at Northwestern. What I'm going to talk about next is very much narrowed down to one particular process called dilute forming process. Okay, so this is the one project, probably span over multiple years. And one of the things that when we look at it, for example, if you look at the Chicago Millennium Park, there are a lot of sheet metals, and it's kind of part of the art. And then these are the double curvature ones, okay? And if you look at the needs for rapid production of sheet metals, you can name it, for example, aerospace is one easy one because their production volume is small. And but then when you also looking at the auto industry, when they look at the prototyping cars, they probably only need to make 100 parts. And then if you want to do it with a die, it's always usually costly and expensive, right? Some of times, we also try to do antique cars, try to remodel that, you have to find the old dies. Or if you want to engrave your own name on the hood, that's another thing, right? So design, repair, decorations, and for the medical, of course, there's also titanium plates that could be used, which could be tailored to the patients, and some of the architecture. The way that's going on, and you probably heard your colleague here also, Glenn, talk about the blacksmith forming. So it's a concept which basically links the materials process to the product. Okay, and what we are trying to do is to automate this process such that it could be used by everyone. Now, start with the material. So today I'm going to selectively talk about some of the aspects, but the focus is also on the functionality through this process. If you look at the incremental forming process, and the old time, of course, it's blacksmith, but then recently you can have these three major configurations. One is single-side incremental forming. Basically, you only have one tool at the top. And the other one is called two-point. I don't know why it's called two-point, but nevertheless, because it has a partial die, it's really not just a point. But you do have a partial die, and then you have another tool coming along. And with this partial die, obviously you can get more complex geometry as well as better geometric accuracy. Nevertheless, you still need to make half. So our trademark is actually looking at the double side. So both sides is going to be controlled numerically. Okay. So we have a video, and it's on YouTube. Let's see whether it's working. Sorry. I don't know whether the sound is working or not. Maybe I can try that. Maybe it's because of me. Okay, you don't get the sound. So, Neil did a really nice explanation on top of this. Another PhD student of mine, so you have to bear with me and just listen to me.
And consequently, has the potential for significant time, cost, and energy savings. Let's take an inside look into DSIF. Just 12 miles north of Chicago, Northwestern is located in Evanston along the shore of Lake Michigan. Northwestern is one of the nation's leading private research universities with annual sponsored research awards in excess of $600 million. The Advanced Manufacturing Processes Laboratory, one state-of-the-art
manufacturing is always in the base.
Initiated in 2007 and built in 2011, our Generation 1 DSIF machine comprises of two forming tools, a command station, and a control system. Currently being built, our Generation 2 DSIF machine utilizes a tri-pyramid design. We're ready to make a part. We begin by designing the part using CAD software. Next, we generate a tool path utilizing scripting routines within the CAD software. Using the finite element method, we can simulate the DSIF process to ensure the prevention of fracture or excessive fitting. Everything looks good, and now we're ready to manufacture the real product. Lubrication is essential to prevent tool wear as well as to achieve an excellent surface finish.
It's not that joggy, the real, it's probably just a video.
During forming, we monitor the forces of the tool tip, as well as the current progress of the tool path. Here's our finished part, and a close-up of the surface finish, and a few other parts that we made.
So this is a flange
For more
basically.
information, check out our website. And thanks for watching.
So here are kind of the collection of some of the parts that we made, and so you can really go stylus. That's our whole concept, and you can also create flange because many of the sheet metal parts actually you need to generate assembly for the other purpose. So you can do the laser cutting, and then you can do that. Now the other thing which is difficult is actually generate something like vertical walls and those features. And you can scale it up and down. So the smallest one that we made is just on the size of the pen. Okay. So when you look at talk to industry, and they say, of course, geometry is geometry accuracy is the number one important part. And now, for people who have been working with metals before, how many of you here have worked with metals before? Okay, all right, just about a third. Now, the part was formed to be a pyramid part, and as you can see, after it's clamped, it was pretty good. When it's clamped. Now we try to take the part outside of the machine, and it becomes I call it potato chip. It's a metal potato chip, and this is really inherited because of the spring back elastic recovery in the sheet. So what you have is, after you release the clamp, and then you have the part is totally unrecognizable. How to solve this problem, right? The way that we did, we actually put the part, assuming the recovery is purely elastic, so we put the part back to the clamp, and then we went through the thermal annealing process, stress relief. And then once you do that, after you take out the part, you see it's pretty good. So we solved that one, and then we say, okay, now the goal is, so these are the different ways you can try to get to the right temperature, arrest thermal annealing. So that's not that difficult, because if we just assume it's purely through the bending process, and you can actually get those parameters pretty easy for different materials. But then we say, okay, now the key part is during the forming, you need to form to the right geometry. And the video that you have seen with the DSF, actually you have two tools, one top, one bottom. That's a simulation model, right? And then you go from the top and then gradually move down. So the tool actually each time is a delta Z going down, and then gradually moving down, and then you see the part gets deeper and deeper. Now the problem with this one is that, okay, you have the local deformation, and what happens is actually when you have a force acting on the part right here, the previous part that you made is also subject to a force. So you kind of stretch it a little bit, for simple geometry, it's easy, but if you have a complex geometry, then it could get tilted or some other way. So the process that we actually developed right here, which is really interesting, is actually we started right, instead of from outside to inside, This one starts from inside and then just push the tool towards the outside. And you see that the tool always on the top of the, kind of the clamp and never move down, while the part actually gets deeper and deeper, right? You see that? So this is interesting because now what you have is you have local deformation happening right here, okay? And because I'm always working with the virgin material, which is the material has not been work hardened, I can have a better control in terms of the displacement because all these materials probabilities are kind of consistent, right? And then I can go there. So nevertheless, if you look at the plot, when we look at the shape deviation versus, for example, different squeeze factor between the tool, and it's kind of busy plot, but bear with me and let me explain that to you. So this is shape deviation in millimeter. And let's just take a look at this red one. Forget about squeeze factor, we're not going to talk about that. But just look at the square ones. Now the gray one right here is the DSIF, which is a traditional one from, when I say traditional, it's really still, actually our group started this. When you have the outside going to the inside, okay? And with the delta Z about 100 micron. And then you can kind of, and this is a part that we made, and then if you look at, compare the part, so the part is not just a simple part, but actually you also have features in there. But the average shape deviation is about 3 millimeters if you do that process, okay? Now you can change the delta Z to be 25 micron, okay? And then you can reduce the shape deviation, all right? Now, if you do ADSF, the one that I told you earlier, from inside to outside, with the tool always at the normal, the initial clamping position, the delta Z is 100 micron, you have shape deviation at just below 1 millimeter. If you go even better, with say 25 micron, you can go very low, it's about 0.5 millimeter, which is, the industry start to take this as okay. Right? They actually want to probably have even less than that, 0.2 millimeter. So, if you go even lower, this is start to getting ridiculous, right? 25 micron, if you get even lower, it takes forever to make it. But the process, you see there are two additional bar right here. And then what we did right here is that we call it MDSF, just a mixed double-side incremental forming. So what we started, we actually use a delta Z as 100 micron, okay? We do ADSI first, basically from inside to outside first. And then the second time we still use a delta Z as 100 micron from outside to inside again. So you can think about the machining process. You can do the coarse machining and the fine machining or do the shaping. It's a similar concept, right? So with this one, even though we do it twice, which means, the time that needed for the mixed one is about twice as this much. But still, it's about half of this much. And then we can get better, geometric accuracy. Okay. So, yeah, that explained. Now, so when you have the geometry, it's okay. And then when you talk to the aerospace industry, they want to know the fatigue, right? You also want to know about that. So what we did, we actually made the coupon, and what you have, this is a simple SN curve. The black one is so-called virgin material, which is not work hardened material, it's our benchmark. And the single point incremental forming is when you only have one tool on the top, and then no back support. And this one is actually down, which means the fatigue behavior is worse. The double-sided incremental forming, the one that I show, is right here. So there's some of the previous work that we did, you can actually understand that because when you do the single point incremental forming, actually you can form, a lot of times you can think about this, is that you don't have that much material drawing. okay? So the formability does get improved, but nevertheless, you have much larger deformation. So if you take the plane strain condition, look at the forming limit diagram, which means the part will fracture or localize before before the localization happened, the strain limit. With the traditional one, take aluminum, for example, 2024, for example, typically it will localize around 20%. Now, when you do the incremental forming one and plane strain, it can actually go to 80% without seeing fracture. So the damage, actually, the mechanics happening in this process has been changed from a localization-dominated fracture to, the failure to fracture failure. Okay, so when you think about then, in addition, I have to throw this because Dave said there's no fundamental slicing process, right? So when you think about this, it's really how do you control the damage evolution in this manufacturing process? So we actually have a paper on this, which I didn't include this, but nevertheless, what you can imagine is here you actually have local voids developed, and the voids, fatigue is very sensitive to voids, right? And that's, when you have this kind of reduced fatigue behavior. Now with the ADSI, because you are putting the compressive stress actually through the thickness, okay, so you're closing that voids and help this to get a longer, a better fatigue behavior. Okay. So surface finish is another issue, and surface finish you can solve it kind of using engineering method. So basically, one of the way to do that is when you do the delta Z, you can adjust that based on the local curvature. Okay, so basically looking at the machining process, it's very much the similar idea. You have scallop two tools coming together, and then you generate to the roughness. So you can do actually pretty smooth if you just do this variable ones, as well as you can reduce the forming time. Okay. I very much talk about the hard materials. When I say soft metals, aluminum could be. When you do the hard one like titanium, and it gives us challenge because our machine has a limited load capacity. So the way that we do it is actually when we have the titanium sheet about 0.5 millimeters. Remember, we have two tools. So what we did is we pass electric current through those two tools and locally heat it up. And then because the local deformation and the amount of the power, the juice that we need is not that crazy as Aaron's slab. The other thing is, if you look at the literature, and one way they talk about using electrical current assisted forming is they say, okay, if you do not have any current, and then if you do the compression test, you see that it fractured this height. If you do isothermal heating, go to the same temperature as the EA, electric assisted one will give to you. It fractured at this point, cracked right there. But if you do EA, it's still okay. So by having this set of the experiment, the argument is that there's a non-thermal, athermal effect will help to increase additional formability of the material. Okay. Now, so when look at this or say, okay, let's think about how we can prove this or disapprove this. One thing that is different when you look at these two tests, EA test is instantaneously because the Joule heating is instantaneous. The isothermal heating is actually you have to put the sample into the furnace for a while before you can do it. So my experiment is actually we developed, we have a small, very small, tiny little bit, a tensile machine right here. And this is really the size, 200 millimeter. And our sample, the sample width is only about 1 millimeter, 1.2 millimeter. And So you can, there's a DIC of course, and then you can look at, even with such a small one, you can actually get the strength field. So the idea that we got is, because the EA is instantaneously happen in electroassisted ones, right? So our idea is the following, saying, okay, we want to compare whether there's additional EA contribution or not. So, but we also want to take the time, the time factor out of this equation. So what we do is we put a tensile specimen and then we pass through electric current. And then meanwhile, instead of trying to compare it to the high temperature, we use an air nozzle to blow the air onto the specimen. Remember, our specimen is very small, so it's very easy to reach uniform temperature almost instantaneously, right? And then you can adjust to the airflow temperature. You know, you can even cool, even high, but there's a limit. It's about 180 degrees, and then that's it. But nevertheless, you know, what we could do is actually we can compare now with the samples with the air current or without. So here are the results. I just brought two cases to make it simple, but actually there are a lot of sets of the data behind it. This is, the dotted one is the room temperature stress strain curve. The triangle ones are the ones with you know, the current density about 16 amp per millimeter square, and also reach to a temperature about 435 degrees C. If we blow the air, okay, right there, what you see that is actually this blue, it went back to the room temperature, while we are still passing the electric current, okay? Similarly, for the other material, it's similar. This is pure titanium, this is aluminum. So our conclusion is that most of this is still thermal, the Joule heating effect, and not too much on the athermal effect, okay? Because if you pass a current, you know, if you have the temperature the same, they are about the same, right? Now, knowing that, why it's important, because knowing that, then we can actually use it very effectively in our modeling. So I think by this time, you know, you probably will be tired of Northwestern purple, so I put some of the Ohio State red here. So knowing this is a purely Joule heating, then what you can do, you can actually use the well-established equations and to find out the delta Z if you add the thermal effect, the electric current density, and then you can actually calculate what the temperature increase is going to be for different material system, right? And then because this is also well established, if you have the temperature increase, you know what is the flow stress, right? How much reduction you have. So this is normalized one. And that's well-established data. You can get it, you know, for different material constants. So when you combine these two together, actually what I can tell now is that depends on what kind of temperature. So this is a temperature flow profile. This is a reduction. And then when I combine all these things together, what I can tell is how much amount of the current density I'm putting in and what is the amount of the flow stress reduction. And you can compute this analytically using existing data. And what's important is actually, because in the literature, people are wondering why they call it so-called threshold current density. Basically, for some material, for example, aluminum, it's almost like nothing going to happen, but then eventually after this threshold, there's a sudden drop of the flow stress. So people were wondering why it's happening, you know, and for this, and some material like titanium, you don't see that much, okay? But then when you put this model all together, you can actually see it very clearly in what's happening right there, okay? And then we compare to the experimental data, you know, and then it's close enough from the first order approximation. So now with that, going back to the incremental forming ones, titanium is very hard to form. So we just want to form a dome. And if you use a baseline room temperature, it fractures right there, okay? And then we put the current in, and then you see actually we are getting better and better. So, you know, and then you can actually also start to work on the product material. Okay. So going back, I probably have additional 7 minutes, right? How much time do I have?
A little more than that, but yeah.
Okay. The other thing with the DSI, remember we have two sides, for people here with a control background, I have to show this, right? So you have two sides coming in with the control. And one thing interesting that this is almost happened by accident. Because we try to make the funnel shape. One side it looks perfectly fine, and then the other side you have fracture. And then when we look at the part, it's really not that symmetric, that we put some symmetric commands into the system, right? So the front end, you see the nice shiny part is right here, which means the tools has been contacted. But then on the back side, it's not, the contact line is right here, and this is fracture. Remember, I also talked about what happened right there is actually you degrade from double-side incremental forming to single-side incremental forming. So the single side, basically only have one tool on the top. So our hypothesis is that if we can maintain the contact, we will be able to delay the fracture. Okay. Now, so this is our hypothesis, and then you actually have to work with the system. One way to do that is really because they are the target trajectory, and then you go to the command trajectory that we change to the tool position. And then when you go into the machine, there's a motion, motor controls the position, which could be different from here. And the other thing is when you form it, the tool itself also, it's an elastic component, right? It could also have some deflections. So there's a system also has a compliance issue right there. So when you have the formed part, which is obviously not the same as the previous one. So one way to do that is you offline compensate. You say, okay, what's the difference, and then compensate that way. Depends on the tool gap that I'm commanded. But that's kind of, not so good. It gives us some good results, but we want to do the real-time process control. So let's first say, okay, whether the offline will work or not. Basically you went to check our hypothesis, right? So this is a Shannon Park that we made, and you see the contact lines like that. So when we say, okay, this is because of the tool compliance, this is kind of an offline compensation, and there's a compensation function right here, which depends on how deep you are, what's the orientation, and what's the local curvature of the material. And then once we put the contact line up, yeah, it does work, right? So you see that, you create a fracture right here, but then once you fully compensated, it was good. So knowing that, then the next step is really, how do you do the real-time control to make sure that everything is going to be contacted? This actually just shows you most of the contact mechanics right there. Okay, so skip that. So we want to do the online. The online, the key thing is actually the compliance. So we think the compliance actually creates the most problems. And then you create the compliance and then you feedback. So the model, the controller is actually pretty easy. We use a traditional proportional integral controller. Nevertheless, to identify the compliance is something that we won't. So after you do that, you can actually do, we use a force control in the radial condition to radial direction, and then give us the contact. So now we don't have to actually look at this real-time, offline compensation. Now we can really do the real-time and also look for different geometries. So, okay. Finally, talking about the machine, you saw the movie, and this is something that we have been working to get the larger one. In terms of the future research needs, some of the additional ones that's happening right now. One is a material constitutive law because we have bending, unbending going on between the tools, and therefore you have the kinematic hardening and all these other interesting stuff happening. So this is something that actually we are working with the Fohan to look at, you know, the double-sided incremental forming, and then you see the force difference. The other thing which is important is actually how do you do this, you know, very sharp part, kind of deep, straight wall. So, and then the unevenness of the thickness distribution. So that's some additional work that's needed. Okay. Microstructure-wise, which is good, you know, when we look at the EADSIF, it actually doesn't change that much for the microstructure. So the other thing that, this is what I said, no option is the best option. If you go to the shop to, particularly, you know, I don't know, there are too many options, I get lost. So no option is the best one. I want to have the turnkey solutions so that everyone can use it. And one of the things is the two-pass generation, which is really fun. Because the conventional, if you think about the CAD software, they doesn't take into account, for example, the local sheet defamation and the other stuff, you know. So we actually have been developing our own C++ two-pass code to consider these effects. And then we have 88 for all these different modes that now you can do that. So right now the code is in the open source code, and everyone who's interested, feel free to contact us. Finally, yeah, education. We put actually the tool to the Chicago IMTS show, which is the largest machine tool show, happened once every 2 years. And then we, you know, those are undergrads working on lab, and then they see, you know, those fancy machine moving. There are a lot of kids over there. So that's a team. And for this particular project, I want to thank some funding agencies as well as the current and past collaborators on this. Okay, so we'll finish right here.
Questions for Dr. Chow?
So I have a question about the increment depth. So I would think, you know, if you decrease the increment depth, then you would increase the surface finish, but it would increase the cycle time.
Yes.
Right. And so how would you normally determine your increment depth?
Right. So there are two different ways you can think about this. So if the part has a specific surface finish, as I mentioned, then we can look at the local curvature and then decide what is the maximal incremental depth we could take, right? So that's one way to do that, if your surface finish is a requirement. Now, if the surface finish doesn't matter that much, actually, for example, the titanium part that I showed, our collaborator in Italy, they actually like to see the rough surface finish because it's an implant. And then they say it's better with the cell growth. So in those cases, then the formability is going to be the dominant limit, right? And obviously, so if you can, the smaller incremental depths and also gives you a larger formability, okay, a higher formability. If that is not a concern, then there's other way is also, then you want to push as fast as you could. That will be the force limit of the machine, right? So if you consider all these things, you can try to optimize the process.
Go ahead. So thank you very much, very interesting work. Just one question which arose for me is that in this incremental forming, it seems that when you're forming a concave feature, you would not be able to have a convex one inside that. Is that correct?
You can do, actually the one that, for example, when we had the pyramid and actually we have the other features really intentionally go to the other direction. So there are another multiple ways you can work on. One is how do you form feature in sequence? You can form it in different sequence. You don't have to form it all in the same time. That's one way. And the other way, you can also change the tool, right? So the tool doesn't have to be 3-axis, you can do 4-axis, 5-axis, many things you can do.
Questions?
So I got kind of two. One, have you tested this against like a traditionally formed sheet metal part to understand what the differences are and the mechanical behaviors of that? So in the automotive space, if you want to use it for prototyping, you want to make sure that it's going to behave the same way as a traditionally stamped part, since that's not going to be your mass production method. So have you done some of that comparison?
Right. So the one I showed is the fatigue, right? So in addition to fatigue, of course, when you have the part, the metal part, which is nice because you can kind of predict that, because what happens is the material still will harden. So you still can predict that will hardening behavior, right? But then, of course, in some way, you also become thinner, right? But as long as you put those information into your model, you can do the crash analysis, you can do, so I don't think that's, it needs to be done, it's just not a roadblock.
Okay. And then the other one is for anisotropic materials. Is there any issue with spring back in multiple directions?
Yeah, so spring back in multiple directions, definitely because of the anisotropic behavior. And the stress relief that we have seen, because it's actually at a very different stress level. So far we are happy with that, because I think the anisotropic probably will create something, but not as dramatic as if you can do stress relief. But not all material can do that. That's a tricky part, so we have material science people here doing it. Yeah.
Just a real quick question on the stylus you're using. I understand it's like a sliding kind of contact. Have you considered like a rolling contact, and have you studied any kind of effects on sensitivity of the process to tooltip geometry?
Yes, definitely. So for example, one idea is instead of spiral type, you can have ball pen type, right? So we actually tried that. We took the ball bearing, which is a really smooth surface, very well defined, and then design a tool holder and put the ball bearing in. It works out really nice for the top tool, or for one tool, because, and then the other way, if you don't hold it well, it actually drops. Now, one thing with that ball bearing ones, and then because you have to have the holder, so there's a clearance issue, because then you can, so it depends on your geometry. If your geometry is shallow, it's okay, but if you want to form a straight wall, then it goes into your clearance issue. But people are trying different, certainly people are trying different geometry, and if you search around, that's an area where a lot of patents try to get into that, because they say, oh, this is my tool geometry, you cannot use it. Right.
So when you're trying to form really hard materials, does the strength of the tool start becoming an issue when you start trying to form out really fine features? Like even when you factor in the heating, at what point does the tool just become so thin it just snaps?
Yeah, so the force that you have seen, it's about 1,000 Newton, which is not too bad for lots of the tool steel. For the titanium ones, we use a tungsten carbide, which is good enough. Yeah. The other way you can do it, as I mentioned earlier, is you can also try to reduce the depth, and then that will lower the force. You add heat, that will really lower the force. So some other people use laser heating or some other, assisted method to soften the material. Yeah. So certainly you need to consider that in your design of the process.
Question in the back.
Yeah, your experiment where you cooled the sample while the current was flowing was very interesting. So with that experiment, have you refuted the so-called electroplasticity effect?
Yeah,
Are there any caveats to that?
right, electroplastic. So my belief is, as far as if you use a continuous current, and I don't believe there's electroplasticity there. Now, some people has tried to use the pulse current because their theory is you have the dislocation and the electron pulse it, you have the dislocation past the grand boundary. To make this happen, I did a back of the envelope calculation. The number of the pulse sequence is so high that the current power supply won't be able to reach that. So it's whether, in general, I think majority you are not going to see electroplasticity. That's my theory. Yeah.
I'm working with capacitor bank supply currents, so maybe there's, so you've not yet said that with the capacitor bank supply you might still have a electroplasticity.
I just don't, because the order is just so much different, and I can't claim that at the other end it's nothing going to happen, right? Just like when we go down to the nano, there are many new things happen. It could happen just at this level that we have seen, it's not there. And this is actually something that NIST was pretty happy with our results, because if you think about the Husky bar, right? The way they heat the sample at a high temperature when they do high strain rate test is they pass the electric current. So they say if this actually changes the material property, all their standards is going to be trouble, right? Yeah.
Have you also evaluated FLDs for these processes? FLDs?
Yes. So FLD, yes or no? Yes, we did evaluate it. It's much higher. So the regular, as I mentioned, is like this, and this is actually way higher. But nevertheless, I would caution you because the filling mechanism is different. It's not the FLD is a localization-driven one, so it's not fracture. So I won't use that entirely. I would think actually a damage-based model would be much reliable.
Thank you.
Jian, do you have a question?
Oh,
Okay.
what are the biggest unknowns in modeling the process? And the reason I'm asking is from a controls perspective, one of the things you try to do is to accommodate these unknowns. Is that a feature of what you've got implemented?
The unknowns are for the lubrication condition, which is still a question in terms of, because you have local contact, you generate very high local temperature, contact pressure. So actually right now we do have a project to look at the contact mechanism around locally too, because that will influence your force and the other control aspects. Lubrication, contact. The other, of course, metal, anisotropic, and all the other things you can throw in the air. Then the challenge is how fast you can compute that in real time. To give you some comparison, experimentally I can finish in half an hour. If you want to do a good capture of the modeling in FEM, it probably a good few days to a week. If you ask Farhan to do the crystal plasticity model, which is even better, you have all these microstructures, you can ask him. He has been running the simulation for 2 weeks and probably more.
And the feedback you have right now from the process for control is really forces
Just
and
force.
motions. That's what you have,
Yes,
right?
yes, that's the force and motions that we use, right.
I guess to follow up on that, is there, you mentioned this kind of spectrum of computations taking weeks to hours. Is there something that, in terms of embedded in your models for feedback control, that are maybe simple first principle laws, that can maybe at least push you in the right direction?
Right.
That you can then run in real time?
That's, my student is finishing his PhD right now on this. That's part of his work, to see the first order.
Okay.
We use the first order. Yeah, the first order it's easy, but the hard part is actually getting So that's implement in the offline and the real time.
In real time, okay.
Yes, yeah. Offline we don't need that. Yes, definitely need that.
Any other questions for Dr. Chen? All right, let's thank this for